In this lesson, we're going to be looking at energy and changes of state, as well as the first law of thermodynamics. And so as far as goals for this, we're going to use heat of fusion and heat of vaporization to calculate the energy transferred as heat and changes of state. And we're going to be able to recognize how energy transferred as heat and work done on or by a system contributes to changes in the internal energy of a system. We're going to calculate the work done by a system by the expansion of a gas against a constant pressure. We're going to calculate changes in enthalpy and internal energy, and recognize state functions whose values are determined only by the state of the system and not by the pathway by which the state was achieved. So first, looking at energy and changes of state. A change of state refers to changes between three states of matter: solids, liquids, and gases. When a solid melts, its atoms, molecules, or ions move about vigorously enough to break free of the attractive forces holding them in rigid positions in the solid lattice. Similarly, when a liquid boils, the particles move much further apart from one another to distances at which attractive forces are very minimal. In both cases, energy must be furnished to overcome attractive forces among those particles. That is a change of state, going from a solid to a liquid to a gas. Now, the energy transferred as heat that is required to convert a substance from a solid at its melting point to a liquid is called the heat of fusion. Solid to a liquid, the energy needed to make that substance go from a solid to a liquid at its melting point is the heat of fusion. The energy transferred as heat to convert a liquid at its boiling point to a gas is called the heat of vaporization. And these are often known values similar to the specific heats. We would look at the specific heat of iron. Well, we know the heat of fusion of iron. These are all known values, or we can calculate it if we know everything else about the problem. So it is important to recognize that temperature is constant throughout a change of state. Okay, during a change of state, the energy added is used to overcome the forces holding one molecule to another, not to increase the temperature. So when we were calculating Q in the previous lesson, we did M times C times delta T, right? There was a change in temperature, but at the melting point, like water, for example, the melting point of water is 0 degrees. And so there is no change in temperature when we are going through the heat of fusion, yet there is still energy required to melt ice at 0 degrees. So here is a figure that's showing the change of state and an increase in temperature as a result of adding energy. So here we have ice, and ice here is melting. So the state is changing, the temperature does not change. As opposed to this, so we can see the difference in my lattice structure of a solid compared to when I have some solid, some liquid. This change of state, temperature does not change. Here I have a piece of iron. It's a solid, still a solid. Temperature is changing. I am adding energy to this. It is heating up from 0 degrees to 557 degrees. Temperature changes, but the state does not change. This diagram gives us a profile of the energy changes occurring as 500 grams of ice at -50 degrees is converted to water vapor at 200 degrees. So this involves a series of steps. Number one, we have to warm the ice from -50 to 0. So this involves a change in temperature. That's step one. Then we have to convert to liquid water at 0 degrees. So then we have to go through step 2, which is our melting. Notice that as we go across our x-axis, this is all heat in kilojoules. So it takes heat to cool from -50 to 0. It takes heat to melt, even though there is no change in temperature. Again, remember, temperature is constant during the change of state. Number 3, we have to warm the liquid to 100 degrees. So this is step 3. Again, there is a change in temperature. Step number 4, we have to evaporate or boil at 100 degrees. Here's step 4. And notice how much energy is required. How much energy is absorbed to boil, but we don't have a temperature change. And then we have step 5, where we have to warm the water vapor to 200 degrees. So here is step 5. So it's very labor intensive to find this out. We can't just do one step problem and do m times c times delta t and do 200 minus a -50. It doesn't work like that. We have to do each step and figure out how much heat is required to go from step 1, and then step 2, and then step 3, and then step 4, and then step 5, and then we add them all together. So here's that problem. Here are the 5 steps. First, we warm it to 0. Then we melt it. Then we heat it to 100. Then we boil it. And then we heat the steam to 200. 5 steps. We will calculate those Q values at each step and then add them together, because my total Q is 1, 2, 3, 4 plus 5, all added together. So let's look at these piece by piece. To warm the ice from -50 to 0, notice that there is a change in temperature here. So we're going to use that equation for, we'll call it Q1. M times C times delta T. Whenever there's a change in temperature, we can use our Q problem that we're used to with M times C times delta T. Now, in the book, they converted it to Kelvin, but we know that 1 degree change in Celsius is equal to 1 degree change in Kelvin. So we don't actually need to use Kelvin. Let's use Celsius. We know that our final minus our initial, so 0 minus a -50 is 50 degrees of difference. So we should get the same answer here. 2.06 times 500, because this is our specific heat, times 500 times 50 should equal 51500. Which is, this is in joules, and then they wrote it in scientific notation. They said 5.150 times 10 to the 4th, which is the same thing. We can keep it in big numbers though. For part 2, we need to melt the ice. Remember, temperature is staying the same here. There is no change in temperature. So to find this Q, we take our mass times the heat of fusion. And the heat of fusion is given to us. These are known values. And so the heat of fusion of ice is 333 joules per gram. So we just need to take the mass of ice that we have, 500 grams, times it by the heat of fusion to get 500 times 333 is 166,500. 166,500 joules. So this is my Q for step 1. This is my Q for step 2. Let's look at number 3. We're raising the temperature from 0 to 100. So there's a change in temperature here. Now, that means that we're going to use our Q equals M times C times delta T. So we have my mass, my specific heat. Now I have Here I have specific heat of water, right? Because I'm at water. We have to use the C of water. Notice up here, I use this, my C was of ice. Again, these would be values that you would be given. I also then need to find the change in temperature. They used Kelvin, we don't need to. We can do our final 100 minus 0, so our change in temperature is 100 degrees Celsius. So if we did 4.184 times 500 times 100, we would get 20921234 20921234 joules. Number 4, to evaporate or to boil water at 100 degrees. There is no delta T here. So we go back to that same idea that we used for step 2. To find Q, we need to take the mass times the heat of vaporization at this point. Heat of fusion was to melt ice. Heat of vaporization is to boil. So our Q for step 4, we'll call it Q4, Q3, Q2, Q1, is our mass times the heat of vaporization. Here's our mass at 500. Again, you would be told the heat of vaporization of water. This is something that you would be able to look up in a table. Multiply these two together. 128. 1, 2, 3. This is my Q4. And then lastly, to get to 200, well, we knew that to boil it was at 100 degrees. So now I need to go from 100 to 200. So my delta T, notice that there's a change in temperature here. We're back to Q5 is M times C times delta T. There's a change in temperature. I have my mass, 500 grams. The specific heat here is of steam. Again, you would be told that. So M times C times the change in temperature, which is 100 degrees. We did 200 minus 100, and we would get 93000 joules. Then, to find my Q total, I have to add up 1, 2, 3, 4, and 5. And you should get 1.65 times 10 to the 6th joules, which would look like 165, 1, 2, 3, 4, 5, 6, or 1,650 kilojoules. And that would just be taking 3 decimal spots off. Our next practice problem is looking at how much energy, the amount of energy necessary to raise the temperature of 1 liter of ethanol, and its density is this. So first I'm going to pause because I know that I'm going to need to know mass. I'm given volume and density. So we know that, I'm going to use this cute little table. Remember that density is equal to mass divided by volume. So how do I find mass? It would be density times volume, right? So let's find mass is equal to density times volume. So let's do its density 0.7849 grams per cm3 times 1 liter. And we know that cubic centimeters is equal to a milliliter. So I need similar units. I've got 1 liter, which is equal to 1,000 milliliters, right? 1 milliliter is equal to a cubic centimeter, and I need my units to match so that I can end up with just grams for mass. So we're going to do 0.7849 times 1,000, so that's going to give me 784.9 grams. Okay, it's a good starting point. So we've got our mass, and we want to raise the temperature from 25 degrees Celsius to its boiling point, and then vaporize it. Okay, so if I'm looking at a graph here, we're starting at 25 degrees, so we're just going to say 25 degrees right here. We want to go to 78 point whatever. There's a change in temperature here. And then we want to vaporize it. Vaporizing, remember, is no change in temperature. And then we're going to stop. We're not going to then heat the vaporization. So this is going to be a two-step process. So first, let's do this step one, where there's a change in temperature. We know that we can do for a Q1, M times C times delta T. So our Q1 is our mass, 784.9 grams, times, now we need the specific heat of ethanol. And it gives it to us right here. Specific heat is 2.44 joules per gram Kelvin, which we also know as joules per grams degrees Celsius. And we need our change in temperature. So let's find out what TF minus TI is. So 78.3 minus 25, 53.3. Okay, now let's multiply all of these together. Times 2.44 times 784.9. All right, I get 102,077.814. So this is our Q1. I'm going to put a box around it. Now we know for Q2, we have to do the heat of vaporization. So Q2, there's no change in temperature, so it's just mass times the heat of vaporization. So Q2 is the same mass that we just had, 784.9 grams, times, we need the heat of vaporization, and luckily it gives it to us. The heat of vaporization at that temperature is 38.56 kilojoules per mole. So it's great that they gave us this heat of vaporization. I'm just going to write heat of vaporization, 38.56 kilojoules per mole. But here's our problem. We want to add up our Q1 and Q2, and we need them in joules. So in order to get joules out of Q2, I need my heat of vaporization to be in joules per gram. Normally, they would not throw us for a loop like this, but we need to convert our kilojoules per mole into joules per gram. So we got to go, okay, what is ethanol? Ethanol is C2H6O. So we need to say, well, in 1 mole of ethanol, what is the molar mass, right? Because that'll get rid of moles, and then I can have grams down on the bottom. So I need to get the molar mass of it, and it should be 46.08. Okay? Then I need to get rid of kilojoules, so I'm going to have kilojoules on the bottom, and I want joules on top. And I know that there's 1,000 joules and 1 kilojoule, so that'll get rid of my kilojoules. So let's do a little bit of quick dimensional analysis here. 38.56 times 1,000. Oh, I only did it by 100. 38.56 times 1,000 divided by 46.08. So we get heat of vaporization. We're converting that into 836.81 joules per gram. We're going to plug that number into here. 836.81 joules per gram. Okay. Well, that took us for a little extra work. Okay. So now we're going to do our mass times our heat of vaporization times 784.9 to get, a big number. Our Q2 is 656808.68 joules. And we know that to find our total heat for raising this temperature and then vaporizing it, we need to do Q1 plus Q2. And when we add up our two values, we should get 759 kilojoules, which would be 759 kilojoules, which is equal to 759,000 joules. All right, let's try another one. Why don't you try pausing the video? This one says, what is the minimum mass of ice? So we're trying to find the mass at 0 degrees that must be added to the contents of a can of Diet Coke, which we're saying is 340 milliliters, to cool the cola from 20.5 to 0. Assume that the specific heat capacity and density of Diet Coke are the same as for water. So density of water we know is 1. Specific heat for water is 4.184. And the heat of fusion of water is 333 joules per gram. See what you can write down that you know. See if you have an idea of where to start. So we have to think about what we know and what we need to find out. All right, so we have ice at 0 degrees. And ice is staying at ice. It's going to melt, but we know that ice is just going to go through that heat of fusion. Okay? We have Diet Coke, our can, and our temperature is changing. So we need to find our Q of the cola, and we need to find the Q of the ice, and we know that there's going to be that our Q of one system and Q of the other system need to equal 0. So let's see what we've got. Q of our cola, we know we're going to use M times C times delta T, because there is a change in temperature for the cola. We know that for the Q of the ice, we need to know the mass of the ice and heat of fusion. Let's plug in what we know for the cola. 340 milliliters, well, assuming that it's the same density as water, it could also be 340 grams. So 340 grams. The specific heat of water is 4.184 joules per gram degree Celsius. And the change in temperature from 20.5 to 0. So final minus initial. 0 minus 20.5 is negative 20.5 degrees Celsius. So we've got that. Now we're going to say plus, we don't know the mass. What is the minimum mass of ice? We don't know the mass of ice. So I'm going to say M times heat of fusion of water is 333 joules per gram. And that's equal to 0. So let's do some simplifying. We're going to do 340 times 4.184 times negative 20.5 to get negative 29162.48 plus, when we multiply these two together, we get 333, we're going to call it M. We'll say Mi for the mass of the ice is equal to 0. Now let's add 29162.48 both sides. So we have 333 mass of ice is equal to 29162.48. Divide both sides by 333. We should get a mass of the ice and that negative was there, so that would be positive. 87.6 grams of ice. So if we think back to what we did here, we need to find the minimum mass of ice at 0 degrees that was going to be added to a can of Diet Coke to cool that Coke from 20.5 to 0. So we know that our ice is at 0 and our Coke is going to cool down to 0. So my ice is not going to raise temperature, right? So my Q for my ice is going to be mass times the heat of fusion. My Coke, however, did change temperature. It decreased in temperature. So we did m times C times delta T, that change in temperature of the Coke. So the Q of the Coke and the Q of the ice is going to equal 0. We know that because no energy can be gained from one and lost by another, but the total energy is constant. So there's no adding, there's no creating or destroying energy. That's why we have it equal to 0. M times C times delta T. And for our ice, we just did mass times the heat of fusion. We had to solve for our M, so we just did algebra to get 87.6 grams. Let's do one more practice problem similar to this. Let's say you want to make a glass of iced tea. You pour 250 milliliters of tea, whose temperature is 18.2 degrees Celsius, into a glass containing 5 ice cubes. Each cube has a mass of 15 grams. What quantity of ice will melt and how much ice will remain floating in the tea? Assume that iced tea has a density of 1, a specific heat of 4.2 joules per gram degree Celsius, so which is the same as water. 4.184 is, we want to be more specific. And that energy is transferred only as heat within the system. Ice is at 0 degrees. No energy is transferred between the system and the surroundings. See if you can set that up. All right, so if we think about what is happening here, we have energy transferred as heat from the tea. We know this because our tea is starting at a temperature of 18.2 degrees Celsius. We're going to add ice to it, so the temperature is going to go down to 0 degrees. Okay, so energy is leaving the tea, right? It's cooling down. And we know that that ice is going to melt. So if I take the energy that's lost from my tea plus the energy as heat expended to melt the ice, we know that that's going to be equal to 0, right? Energy cannot be created or destroyed. So whatever energy is used to cool down the tea is going to be used to melt the ice. Those two are going to equal 0. So since we have a change in temperature of our tea, we know that we're going to do m times C times delta T to find this bit. Plus, we have ice. All we're doing is going through a phase change. So we need to do mass times the heat of fusion equals 0. So now let's plug in what we know. We know that we have 250 milliliters of tea, and everything said to assume density of water. So if I have 250 milliliters, I have 250 grams. Times specific heat of water, 4.184 joules per gram degree Celsius. Change in temperature, final. Again, we started 18.2. This was my initial. We're going to 0. So 0 minus 18.2 would be negative 18.2 degrees Celsius. That's my T. Plus, now, we were told that we started off with 5 ice cubes, each one with 15 grams. But I want to find out how much ice will be remaining. So let's just say, I don't know what my mass is, but my heat of fusion of ice, we know, is times 333. That's joules per gram equals 0. Let's find out what this mass is, and then we can subtract from how much I started with initially, because I know that I started with 15 times 5, which is 75 grams of ice. But I know that some of that's going to melt. So we'll figure that out when we solve for m. All right, so let's do some simplifying. We're going to do 250 times 4.184 times negative 18.2. Negative 19037.2 plus, again, we're just going to say 333m equals 0. So I'm going to add that to both sides and be left with 333m equals 19037.2. Divide by 333. M is, and again, I'm just going to assume that that negative is going to fall off here in a second, divided by 333. So I get 57.2 grams of ice melted. Melted ice. I know that I started with 75 grams of ice. My question is asking me what quantity of ice will melt and how much ice will remain floating in the tea. Well, I know that 57.2 grams is going to melt. So how much is remaining? I'm just going to do 75 grams minus 57.2 grams and get, let's see, 75 minus 57.2, get about 17.8 grams of ice remaining. Good work. Let's try this problem. What is the heat of fusion of lead? If 6.3 kilojoules of heat are required to convert 255 grams of solid lead at its melting point, why don't you pause it and see if you can find out? Remember, if we're looking at heat of fusion, that's mass times heat of fusion is equal to Q. So if we're given Q at 6.30 kilojoules, first thing I'm going to notice is that all of my answer is in joules. So I'm going to make 6.30 kilojoules into joules. So that would be 630,123 joules is equal to 255 grams times my heat of fusion. So I just need to divide both sides by 255. 6,300 divided by 255 should be 24.7. I hope you got the same answer. So I have two more practice problems for you to try before we wrap up this section. Why don't you read this, pause the video, I'll give you the answer on the next slide. Hopefully you got this answer. And one more. Find the amount of energy as heat. And hopefully that one was pretty review. All right, well, good job on this section, and we are moving on to the first law of thermodynamics.